Hello everyone, my name is Anthony Shivkumar, and in today's video we're going to talk about the internals and working of MOSFETs, or the characteristics that you want in a MOSFET specifically for or in an application of controlling your brushless DC motor. So in order for us to control a brushless DC motor, the most important characteristics or the most important component that drives the brushless DC motor are your MOSFETs. And what I have over here is a NXP pre-driver. I'm using the same pre-driver. This is my custom fabricated board. This is an NXP design board. But the commonality in any motor control, brushless DC motor control, are these devices, that is the MOSFETs. The MOSFET that I use is slightly different than the MOSFET that is used on this board, and there's few differences. And in this video, we're going to focus on how do you actually select the MOSFET, what should be the voltage rating, what is the power rating, and more importantly, how does a MOSFET actually work? How do you read the data sheet of a MOSFET? How do you make sense of whether this MOSFET is suitable for your application or not? And all of the internals will be covered in this video. So let's get started. So in this video, we are going to talk about the internals working of a MOSFET. And there are a few things that I would like to, that you would learn from this video. One is the basic physics of a MOSFET. Now, we're not going to go into the semiconductor device per se, like manufacturing of MOSFET or the physical, the physics and the quantum physics level of, how all these materials work and how do you build your transistor. We're not going to go into that low level. We're mostly going to look at it from what are the important features that you want to know or you need to know, the ways of working of a MOSFET that can help you design a better circuit or a better brushless DC motor. So we're not going right into the fabrication of, that's more of the physics side of things. We're talking more about the application side of things. We'll talk about the characteristics of a MOSFET, what makes a MOSFET different from other transistors that are out there, like IGBT, BJT, or silicon control rectifier like SCRs. We'll try to understand datasheet parameters. So when you have a MOSFET and it's got a couple of, the MOSFET that you've selected, there are a lot of parameters that the manufacturer provides. How do you make sense of that? And lastly, we'll try to focus on how you can select the right MOSFET for the BLDC application. Now, this is going to be a 2-3 part series of lectures or presentation. And this is going to talk about really, everything you need to know, at least for the most part, in terms of, how to select a MOSFET and use it for your application, specifically for brushless DC motors. Okay. So how does a MOSFET work? In the simplest of form, it is a switch. And the full form of a MOSFET is a metal oxide field effect transistor. And to give context, if you apply a particular voltage at one of its terminals, then you can make the MOSFET conduct within the other two terminals. So it's basically like a switch. And if you don't apply voltage in one of the terminals, then you have an open, something of that sort. So the three terminals of a MOSFET are known as drain, gate, and source. And the controller, or the controlling pin that basically allows you to control whether you want the MOSFET to conduct or not conduct, is the gate. Now, looking at the right, the MOSFET is controlled by voltage, right? Unlike BJTs, which can be controlled by current, MOSFET is predominantly controlled. The gate, you apply a voltage, and the voltage that you apply will determine whether your MOSFET can be in conduction region or whether it's not conducting at all. The three terminals of the MOSFET, which is basically the drain, gate, and source, if it's not conducting, you're basically not, there's no conduction between the drain and source. So that's technically an open. And once you apply a gate voltage, then the P body breaks down, and then you'll have a short, or in the sense that it'll start to get into conduction mode. Now, there are a few things to note in this particular diagram. One and foremost, that the MOSFET has a couple of it behaves more like a, what do you say, it does have components of a diode in it. It has components of a BJT, or characteristics of a BJT in it, or characteristics of a diode in it. It does conduct even bidirectionally. That's called, it has an integral diode where you can have current flowing from source to drain as well. This is very important in terms of, especially in few power electronic circuits where you want the MOSFET to, or you want the circuit to conduct in both directions. You don't need to have an additional device connected to your in your circuit. The MOSFET can basically allow you to conduct bidirectionally. But we will focus a little bit more about this diode later on. But in here, we're looking at, the drain is the bottom. So the drain is this pin. The top part is the source. The source is basically this pin. And in the middle, you have the gate oxide, or the gate conductor. And as you apply more and more voltage, it breaks this down. It breaks down the body. And then you have a conduction region between drain and source. And that's what you have over here. And when there's no voltage applied, then there is a barrier. And once that barrier is, I'm trying to simplify the concept. I don't want to get more into the technical about doping and, how the PN, junction works and stuff. That gets very much into the physics of the MOSFET. All I want to make sure, the way I want to explain is basically saying that you apply is something that can be practical. When you look at a MOSFET, you understand the internal workings from an application standpoint. You don't need to know the details and the physics behind it. So in a nutshell, these three terminals. There is some form of capacitance or a parasitic capacitance we'll be talking about in this particular video at a later slide. But what you want to note is that this is a voltage control device. It is bidirectional in nature, and if you want to conduct, and if it needs to conduct between drain and source, you need to control it through the gate, and the voltage you apply at the gate terminal will determine how much of current can flow from drain to source, or how much or what is the resistance that your drain to source might have, and whether it will conduct like a short circuit, or whether it's going to dissipate a lot of loss. All of that will be described in this in future slides in this video. There are two symbols for a MOSFET. One is the enhancement mode and one is the depletion mode. Most MOSFETs that you would be using for applications will be in the enhancement mode of the enhancement mode MOSFETs. And in a nutshell, just think of it as that enhancement mode MOSFETs, that if you apply the amount of current that can flow from drain to source is kind of directly dependent or correlated with the amount of voltage applied at the gate terminal. It's not, and that's really what an enhancement mode MOSFET is. And the symbol is slightly different as well. You'll see like these three are basically, there's an isolation between here, whereas here, if it's a depletion mode, there is no isolation. So most MOSFETs you're dealing with will be enhancement mode MOSFET. And the MOSFETs that I showed you earlier in this video are all enhancement mode MOSFETs. As I mentioned, we're trying to understand a MOSFET from a practical perspective. So if you apply gate voltage, you'll have it'll be in conduction mode. But this is an ideal MOSFET, right? A practical MOSFET has other issues that you might want to consider. And some of those issues are parasitic components or parasitic elements. And what are the parasitic elements? One of the parasitic elements of these MOSFETs is that it has capacitance across all three terminals. So it has a capacitance across the gate and drain. It has a capacitance between gate and source, and it has a capacitance between drain and source. So all three terminals, there is some form of capacitance, and that's how what is described in this particular picture over here. So ideally, if you have your gate source voltage exactly as the drain source voltage, that will be an ideal situation. And here you have your voltage across drain source. Then the capacitance is almost, they both are kind of, the equal. The gate to drain capacitance is in a good state. But once the voltage to drain to source increases, then the capacitance can, is not in. In the actual diagram, it'll be a little different. In the actual or a practical MOSFET will be a little bit different. So parasitic components of a MOSFET is also described in the data sheet, and you want to consider this because it will affect things like, how quickly you can switch. How do you, capacitance can slow down the circuit as well, right? Like if you apply a particular gate voltage, what is the rise time? What is the fall time? All of those components, are affected by these parasitic nature of these of the MOSFET. What we also have over here is there's something called as the Miller effect, and that's also affected by the capacitance, the parasitic capacitance. So what we have over here is a capacitance across the gate to drain. We've got a capacitance between gate and source, and we have a capacitance between drain and source. All right. So these are parasitic elements. One of them is the input. The input capacitance is the gate to source capacitance plus gate to drain. So the total capacitance at the gate, between the gate and drain and gate and source, is the input capacitance. The output capacitance is between the gate and drain and source. So you're basically looking at the output capacitance is the capacitance between the gate and the drain and source. And then you have the resistance or the conduction period capacitance. Then that's basically the capacitance between the drain and in the on period or during the conduction time, you generally would have with the gate and drain capacitance must be equal to the gate and source capacitance. So these are the parasitic elements, and this is all mentioned in the data sheet. There's also parasitic resistance. And what do you mean by resistance is when your MOSFET is in the conduction mode, when there's enough gate voltage and your MOSFET can now conduct. It is not ideal. It's not that there is no resistance. There is some form of resistance, and it's the resistance that are basically called parasitic resistance because they shouldn't be there, but they are there. And what do resistance do? They basically limit current. They can, have an I square R loss, and they can generate heat. And this resistance is what is also the reason why MOSFET is a majority carrier device. And what that basically means is that there's it can be either a P-type or an N-type. In this particular case, mostly you'll be using an N-type MOSFET. And an N-type MOSFET is, in a simple English, is if you apply, it's always off, generally speaking, till you apply a gate voltage. And once you apply a gate voltage, then it turns on. And once it turns on, there's only, whereas if it was and it's because of this that it's causing that it has a resistance. Now, there are certain parameters or certain aspects of a majority carrier device. One and foremost, it has high switching tolerance. It has high switching capacity. Like you can switch very quickly, but it also has a resistance. And that's the reason why a MOSFET is used for brushless DC motor, but you want to take care of the resistive nature when it's conducting. And all of these parameters are important when you look at the data sheet. And also you want to know how much heat is dissipating from your MOSFET. This is the kind of information that is relevant when selecting a MOSFET. So you always want to know what's the turn on voltage of your, what's the resistance that is there when your MOSFET is on. This is what this parasitic resistance is. It shouldn't be there, but it's there. Let's look at the IV characteristics of the MOSFET. IV characteristics is nothing but current and voltage characteristic. And there are three regions in which your MOSFET basically operates. There is the active region, and then there's the ohmic region, and in this particular region you can basically say it's basically off. So on the right axis we have voltage of drain to source, And that'll be the value of your MOSFET, your typical rating of your MOSFET. And the MOSFET that I've just showed you earlier in this video was a 30 volt MOSFET. It was rated at 30 volts. So if you go beyond 30 volts, you're going to have an avalanche breakdown and you'll burn your MOSFET. So you don't want to go beyond the typical rating capacity. In the y-axis, you have something called as ID, which is the drain current. And what the drain current does, it basically is the amount of current that is flowing from drain to source. And in the middle graph, you have gate to source voltage. And the gate through source voltage is the amount of voltage applying at the gate. So as you can see, if you don't apply enough gate voltage, your MOSFET is basically off. Like there's not much current flowing through it. And as you apply more and more gate voltage, then you reach an active region. And if you apply a very high gate to source voltage, based on the ratings of your MOSFET, you will reach an ohmic region, or very similar to a short circuit. And that's what you want. Basically, it's conducting. And if it's not in this ohmic region or active region, this area, if your MOSFET is operating in this area, it will cause a lot of loss, because now you're not operating at its full capacity. There'll be a lot of switching losses, and it will dissipate a lot of heat, and you might, damage some of your components. So this, and it'll also, it'll make your speed controller extremely inefficient. So you need to know how much gate voltage you should be applying so that your MOSFET is operating at an efficient rate. And these are the characteristics that you want to look at the data sheet when you're selecting your MOSFET, so that you know how much gate voltage you need to apply to your MOSFET. And your microcontroller directly cannot apply that voltage. You need to have some form of a pre-driver or some form of a voltage amplifier that can power and drive your MOSFET. And that's why you need a pre-driver, because you don't want to operate it in a place or in an area or in the part of the graph which can make your MOSFET extremely inefficient. You want to operate in the ohmic region where your MOSFET can be operating at a very efficient rate. So let's recap what we have learned today, just to get a sense. First and foremost, MOSFET is a voltage control device, which means you have to apply voltage in order for you to start making the MOSFET conduct. It does have parasitic elements, and one of them is the resistance. It's an on-state resistance, and it actually has a pretty high on-state resistance. And when you have an on-state resistance, you can have I2R losses, and you'll also have a voltage drop. A MOSFET is bidirectional. Current can flow, in both directions due to the body diode, and it's applicable in many power electronic circuits. But in using it as a brushless DC motor, we don't really need it to be bidirectional. We just need it to be unidirectional. And the reason why it will always flow unidirectional is because the drain will always have, generally speaking, should always have a higher potential than the source. So the diode will always be in a blocking state in the applications that we are basically using the MOSFET for. So we will not see basically the bidirectional nature of the MOSFET, though the MOSFET has bidirectional capabilities. There are three capacitance in the MOSFET. There's gain to drain capacitance, there's gate to source capacitance, and there's capacitance between drain and source. And all three are important to understand, especially when you're looking at transient conditions of the MOSFET and what kind of effects it can have in terms of rise time, fall time, when you're switching the MOSFET, and understanding, what's the maximum frequency at which you can operate the MOSFET. MOSFET, based on the IV characteristics of the graph, we realized that the MOSFET can work in a very inefficient state if it's not in an active region. So once it crosses a threshold, then it will always be on. And just because it crosses the threshold does not mean it is operating efficiently. You need to be cautious as to how much gate voltage you need to apply in order for your MOSFET to run efficiently. And that's exactly what my point is. You need to provide some sufficient gate to source voltage so that you can drive your MOSFET in the ohmic region. And that's really why we're studying the characteristics of this MOSFET. And this is particularly this video is so that when you're designing a brushless DC motor or speed controller, you are able to utilize or operate your MOSFET in the right phase, in the right region, so that you can minimize losses, minimize heat, basically. In the next part, we're going to talk more about the switching characteristics of a MOSFET and how this is also important. In the switching characteristics of the MOSFET, we're talking about, the transient conditions. When you're switching, how does your MOSFET go from 0 volts all the way to, say, 5 volts or 10 volts, 30 volts, based on, certain inputs? And is it going instantaneously? No, it's not. There is some form of, rise time. There's some form of fall time. It's clearly in the nanoseconds, beyond, what you and I can see. But in power electronics, everything, or in electronics, everything is, in switching very, very quickly. And in those transient conditions, there are certain parameters that we want to focus on. And that will be the topic for a next video. But I'll still recap as to, what we will be studying around that. In the next video, I'll talk more about this graph, about the transient condition switching characteristics of the MOSFET. I'm not labeled the graph in this particular, in this particular diagram right now. But what happens when you apply a gate to source voltage? What is the effect of what's happening? There's something called as the Miller effect, and I'll talk a little bit more about the Miller effect. How does current go from drain to source? What is the reverse recovery time, and why there's a sudden peak and an offshoot over here? And when there's voltage drain to source, why doesn't what happens during the Miller effect time? What happens when during conduction time, and what's happening and between once it's turned off? We're looking at the fall time and the rise time, and how you can look at a data sheet and understand what parameters and how you can draw your own graph based on the characteristics and parameters that is provided to you by the MOSFET manufacturer in the data sheet. And based on that information, this graph will make a lot more sense, because once we start explaining the graph and what each one of those meanings are, parameters are, you can look at a data sheet and understand what that really means. So to give context, what I have over here, I have a PSM4R030 YLD. That's the MOSFET that I used in one of my brushless DC motor circuits. And this is the motor that we're going to look at the data sheets and try to make sense of the parameters. So I've already downloaded the data sheet in this particular tab over here. And the data sheet will basically give you all the graphs that we just spoke about. And we'll look at one thing that we can look at is the graph that we spoke about a little earlier. I did show you this graph in my presentation earlier. And let's have a look. For this particular MOSFET, we have the drain to source voltage. This is very similar to this graph that I showed you in here, which is this graph over here. And when you look at your MOSFET data sheet, this graph is also over here. And here you can see this is the ohmic region. This is the active region. And here you're looking at, you can be on, you have some gate voltage, but gate and drain source voltage, but it's not going to be efficient. So you have the voltage of drain to source, which is in this particular case is 2 volts. And here you have the current that can flow through is 100 amps. And you can only, if you have 2.4 volts at the gate, the MOSFET is basically turned off. 2.6, 2.8, 3 volts, you're basically turned off. It's at 3.5 to 4.5 volts when you've got, your MOSFET is now technically turned on and is operating at a much more efficient state than, say, at 3 volts. But at 10 volts is when you're reaching that ohmic region. So for this particular MOSFET, if you want to be efficient, you want your MOSFET to be operating at very high efficiency, then you want to basically apply a voltage of 10 volts or more. And that's what this graph tells you, so that you can minimize switching and the on resistance. So that's one graph that you can look at. Another graph that you might look at is as you increase the gate to source voltage, you can see how quickly the resistance between drain and source minimum goes low. So at 2.5 volts, basically your MOSFET is not even on. At 4 volts, your MOSFET is on, but it still has a very pretty high on resistance. But as you start to increase gate and source voltage, it's around the 10 volts 10 volts of gate to source that you're basically reached you're starting to reach the minimum amount of resistance that your MOSFET will technically have during its operating state. All right. So the manufacturers will provide all these data, and my goal over here is to make sure that you can make sense of this data, so that when you're designing your own driver, you have the ability to look at the data sheet and say whether this MOSFET is right for you or not. And if you're selecting a pre-driver, you know what pre-driver you need that can power and support 10 volts, so that it operates at an efficient ohmic region. If your pre-driver can only support say 7.4 volts, then it's not going to work, or it's it'll work but it won't be efficient. So those are the kind of things you can make sense of if you know what to look for. In the next video, we will talk more about these parameters. As I mentioned, there is the Q parameters. These are the dynamic characteristics of this is the capacitance. So gate to source charge, total gate charge, input capacitance, output capacitance. We did speak about this is the reverse transfer capacitance, the RSS. And then we have the turn on delay time, rise time, and we'll make more sense about all of this. What is the plateau voltage? This has got to do with Miller effect. And once we understand what these parameters are, we'll try to not just draw the diagram, but we'll also try to make sense from the data sheet. And eventually, if we can get an IBIS model or the IBIS model of one of these MOSFETs, we can do some basic simulation to figure out, how it behaves when you apply, say, a step response or say, and the switching characteristics of the MOSFET in simulation. That's all there is for me. I hope this video made sense. If you have any questions, you can comment below. I highly recommend you to subscribe to this video channel. Moving forward, I'm going to go more in the direction of focusing a lot more into switching characteristics, PCB design, primarily of designing brushless DC motor. We'll be designing IMU sensors very quickly too. How do you design your own design a bigger board for your accelerometer gyroscope. We'll be starting to do more of the advanced control system algorithms. But in the next few phases of this video, the next few phases, I'll be talking more about designing your own brushless DC motor. We'll be testing a few of those components shortly, and from there we'll try to eventually make the quadcopter fly soon. But some computer vision, artificial intelligence, and some very cool stuff. So hope this video is interesting. Everything that I speak about, from the electronics right to the application to the practicality, is all focused on designing a quadcopter, but also understanding the physics behind it and building your own circuits right from the grounds up, so that one, you can build your own drone the way you want to, but also if you're looking for a job in power electronics or something of that sort, this type of knowledge is very important. Many do-it-yourself hobbyists generally don't go so deep, but if you want to make something practical and useful, having this knowledge is a whole lot of can make a whole lot of a difference. So having said that, do like this video, do subscribe, and until next time, stay safe.